Hi, good afternoon, and welcome to our first Algorithms and Data Structures lecture today. We had a lab session earlier today in which I provided an introduction to Python. I'll speak more about the organization in this course later today. We will first start with a motivation, why this course is actually important and what the course is actually about, and we'll talk about the organization. Concretely, in this course, I will provide you with an introduction to algorithms and data structures, which is probably one of the key courses you need to take in your first year when you study computer science, because we will discuss how we can design our own algorithms and data structures and how to make sure they run efficiently. And today we will have the introduction to this course and talk about some of the goals of this course, some some initial terminology. We will also discuss the organization of the course, and then we will look at graphs, which are a highly generic data structure. And we will look at what graphs are useful for, what we can use them for. We will discuss some graph algorithms. And then essentially all the other data structures in this course are just some type of graph with certain constraints. So we will look at lists, which are a very simple data structure. And in order to build lists, we also want to build them efficiently. So we first need to look at complexity analysis. With complexity analysis, we can determine if certain operations are efficient or inefficient, and we can think about how to build more efficient operations. And then we do the lists, and there will be more data structures like trees and maps and hash tables, which are also just some type of graph with certain constraints. But in order to continue after lists, we need to look at a very important concept called recursion. Some of you may have seen recursion before in your first year, that a function can call itself, which is super important because we will also be dealing with recursive data structures like trees, for example. But when we do recursion, we will also see we can use recursion to sort data sets very efficiently. That's what we will look at. We also see how to search efficiently in data sets. And then we look at trees, maps, and hash tables, which are more advanced data structures. And then we will essentially have everything in terms of the foundations that we need, but there will be time left to do some more advanced topics. So there are some numerous selected algorithms that we will discuss. Probably not all of them in that chapter, but depending on how much time we have left as the term progresses. And then most things you would typically learn in an algorithms and data structures introductory course is methodology from probably the 1960s, 1970s, maybe some 1980s. And those are very important algorithms and data structures, but there is new stuff as well. And that's why we will look at quantum computing. And quantum computing is a totally different approach to solving certain computational problems far more efficiently. And we'll be looking at that at the very end of this course for 1 week as an outlook. So this is what we will do. That's our roadmap. But let's maybe motivate this course, why this course is so important. You have learned in your first semester how to program. And now what do we need to do in order to write somewhat sophisticated software? We need programming as a foundation, but in order to build somewhat sophisticated software that does something sophisticated, we also need to know how to build our own algorithms. And algorithms typically operate on data structures. So data structures store data, and algorithms allow us to manipulate that data. And both of that needs to happen efficiently. In order to build efficient algorithms and data structures, we need more than coding. And now you will actually see what you need all your maths for that you learn in your first and second semester in linear algebra and calculus. We'll need that in order to build more advanced algorithms and data structures. For certain algorithms and data structures, you also need to know more about statistics and probabilities. We will need statistics and probabilities a little bit, but not too much yet in this course, because this is something that you will learn also in greater detail later in your studies. So this is what we actually need to build sophisticated software, and this course will focus on algorithms and data structures, and it's quite a maths-heavy course, so there will be lots of mathematics, which is essential in order to build efficient algorithms and data structures. Before we look at the organization and some more details of this course, I actually want to start with a few definitions. So what is actually an algorithm? There's a very good book from Goodrich. I'll talk about the book later, and I briefly mentioned it today already in the lab session. The Goodrich book is phenomenal, and it provides also a definition for an algorithm. And Goodrich says that a algorithm is a step-by-step procedure for performing some task in a finite number of time. So we have some task, something we want to do, and we want to do this step by step, because the algorithm may contain multiple steps, and this should take a finite number of time. What do you think about this definition? Is it clear to you? Do you agree with it? Is there something maybe you don't like about it? If you see anything that you feel positive about it or negative, maybe send some reactions, thumbs up, green sticker for positive, red for negative. Or maybe turn on your mic and communicate with us, or send something to the chat. So only positive reactions. One thing that could be a bit critical is the finite number of time. The question is, what does that refer to? So it would refer that the algorithm does not run infinitely, and at some point it will just come to an end. And this is actually the point where I'm also a bit skeptical about this definition, because some algorithms, you can keep running them and they could run forever and they return better and better results the longer they run, for example, certain optimization algorithms. But at some point, you need to abort them when you're okay with the result. So this could be something that I'm also not too happy with in the definition, but it's okay. So I've been teaching this course now for 5 years. I started teaching this course here 5 years ago when I started my professorship. So it's the 6th time I'm now starting to teach this course. And when I created it, I looked for a couple of other definitions. For example, I looked at Wikipedia, just as one example. And it says an algorithm is a finite sequence of well-defined computer implementable instructions, typically to solve a class of problems or to perform a computation. So we want to solve a class of problems or run some computation. It must be a sequence of well-defined instructions, so no ambiguity. We clearly need to know what to execute, but these instructions would also need to be computer implementable. So something that actually needs to be able to run on a computer. But sometimes we have purely theoretical algorithms and like maybe some quantum algorithms for which at the time they were proposed, there were no quantum computers yet. So that's why I'm also a bit skeptical about computer implementable instructions. I personally would not frame it this way. Something that I created, and I wondered how would I actually define what an algorithm is when I created that course, and I said it must be a finite, unambiguous, and effective step-by-step procedure for performing some task. So some task, the instructions or the step-by-step procedure must be unambiguous, so the computer clearly needs to know what to execute. And the instructions, the number of instructions must be finite. So the step-by-step procedure, so the description of the algorithm must be finite. yet the algorithm may run forever. And effective means to me actually things that are executable. So not just things that are made up, but something that actually can be executed, provided we have a computer available. There's a question here in the chat. If there is a whole space of ways to perform one task, maybe you can elaborate a bit what you mean with this question, and that would help me. Too ambiguous, yeah. Ambiguous here would mean, or unambiguous would mean that clearly we have defined our step-by-step procedure, that it's clear that the computer what a computer would do, that there's no ambiguity what my statements mean. So it's clearly and well defined. So some people would also maybe not say unambiguous, but well defined, but like it was here, well defined. So this would be more or less what we mean by unambiguous. So these are some definitions that are quite short and simple, but there are more. For example, I found on the internet a definition that says something like an algorithm must satisfy 5 properties. I saw the questions in the chat. I'll refer to them in a moment. And the properties of the algorithm would be an input, what we put in, so which elements, which type, what amount of elements, that we generate an output, so we would specify what the output of the algorithm would be. And then there is this term definiteness, which means that the algorithm must be clearly defined and detailed, so well defined maybe. Effectiveness would mean must be doable and actually effective. And finiteness would mean the algorithm must come to an end after a specific number of steps. Again, this is a bit unclear if finiteness refers to the running time or the description of the algorithm. I'm not saying that any of these definitions is fully wrong or fully right. It's just to show you a selection how other people would define what an algorithm is. And you see all of these definitions have something in common, but also some differences. And this one is certainly the longest one. And one question here is in the chat that it's not just a list of tasks, but something that is actually possible to execute. Yes, a clear description of what to do that can be executed. So these are definitions of algorithms. And you are surrounded by algorithms all day long. Algorithms change our life massively. For example, Quicksort is an algorithm that we use to sort lists very efficiently. It's one algorithm we're actually going to study in a couple of weeks, while the binary search is a highly efficient algorithm to search in sorted data. All of us in the back end with a lot of algorithms that we use, like neural networks, whatever, in the background, oftentimes they are realized through matrix multiplications, where matrix multiplications are used in graphics, for example, in computer graphics. And in order to multiply matrices efficiently, there is, for example, the Strassen algorithm and others. These are some example algorithms that we deal with every day. And now I want to know from you if you know any other algorithms that you have heard about. Maybe simple ones, maybe more advanced ones, and I'd like to collect them here with you in the chat. So whatever you see, please, or whatever you know, please send some names of algorithms here to our chat. So one person refers to Shor's algorithm, which is a quantum algorithm, sliding window. Multiple refer to Dijkstra for routing. One person refers to gradient descent, which is for optimizing. Many students refer to Dijkstra, so that sounds great. These are some great examples of algorithms. For example, there are more algorithms that allow us to train a neural network, just for example, gradient descent combined with backpropagation. One student referred to A star. One student wrote in bold in the chat BOGO sort. We'll see in a few weeks' time what's BOGO sort actually. It's more like a joke, but it's something we'll see in a couple of weeks. There are algorithms for anomaly detection and many other ones. Now, and some people refer to another algorithm here that I will not read out from the chat now. So, but thanks for all of these suggestions here, which chats sorry, in the chat, which algorithms you know about, and you'll learn many more in this chat, in this course, not in this chat. Now, we can classify algorithms, and there are lots of criteria we can use for classification, and I just want to show you some of the most essential ones. One distinction of algorithms is whether they're deterministic or non-deterministic. Non-deterministic algorithms are sometimes also called stochastic algorithms. So a deterministic one means you put in the input, and each time you put in the same input in the algorithm, you will get the same result. For example, adding two integers, that's deterministic. But there are also lots of non-deterministic algorithms for which, when you have the same input, they may give you a slightly different result. Such algorithms are sometimes used, for example, for optimization techniques, like, for example, when you train certain machine learning models. Often, for example, you train a neural network. That's something that is non-deterministic because it has to do with the optimization problem. And there are other non-deterministic algorithms. There are even some, like when you want to sort a data set, there are deterministic algorithms, but there are also non-deterministic ones. And when we do sorting, we will actually compare deterministic ones to non-deterministic ones. And we will actually see how they behave and what difference this may make. So, there's one person that asked about the simplex method. I'll talk about the simplex method probably later in this course, so I'll skip that question for now. But this course will largely focus on deterministic algorithms. We have some non-deterministic ones, but they will not be the focus of this course. Another dimension among which you can classify is whether an algorithm is iterative or recursive. Recursive would mean we use recursion in an algorithm so that a function calls itself with certain conditions, or we could do this in an iterative way using a loop. You can convert between iterative and recursive algorithms, but sometimes for some problems, it's easier to solve them in a recursive way. Sometimes it's easier to solve them in an iterative way. This is something we will both investigate in depth in this course. Then another distinction is whether the algorithm gives you an exact result or an approximate result. For some problems, they're very easy to solve exact, like adding two numbers, sorting something. But sometimes for certain problems, you need approximate algorithms because some problems are just very, very tricky to be solved in an exact way. And maybe very quickly, we can approximate the result. Then there's another distinction, whether an algorithm is serial or parallel. So serial means we have one thread, one process, and we run this on one core, while parallel algorithms would mean that we do work in parallel through multiple threads. And distributed goes even further so that we not only run all of this on one machine, but on multiple machines in parallel. In this course, we will look at serial algorithms most of the time. There will be a little bit of work on parallel algorithms, but it's not the focus of this course. So what we will do is largely deterministic, serial, and exact algorithms that are either recursive or iterative, sometimes non-deterministic, sometimes approximate, sometimes parallel, but they are not the focus of this introductory course. So remember this classification of algorithms. Now the course is called Algorithms and Data Structures, so we should also briefly discuss what a data structure is. A data structure is referred to as, in the Goodrich book, as a systematic way of organizing and accessing data. So we store data and we need some systematic way to access, organize the data, edit, manipulate it, delete it. This is meant by organizing it. Wikipedia says a data structure is a data organization, management, or storage format that enables efficient access and modification. So I agree, we want to organize, manage, and store data and access and modify it. But a data structure not always is necessarily efficient. We want efficient ones, but I would not add efficient to the definition of a data structure. And there are numerous data structures that we will discuss in this course, like lists and trees. We will briefly look at more advanced trees like a B tree. We will discuss stacks and graphs. And all of these data structures here are eventually just graphs with some constraints. If you know any other data structures, please send this to the chat. I'm curious to see if any of you know other data structures and we can discuss them. One person mentions dictionaries. That's fine. We've discussed them in the intro to Python very briefly. Hash maps, dictionaries, hash maps, either two synonyms or two very closely related concepts, depending on your source. Linked lists, it's a variation of lists or some other way of implementing lists. So thanks for those, and you will obviously see many more data structures in this course. And all of us use applications that take advantage of some somewhat sophisticated algorithms. For example, many of us use voice recognition, which is in fact quite a complex algorithm, or there are complex algorithms for voice recognition. We make online payments. We want new friends recommended on social media. We may want to play chess against a computer. We may want to do optical character recognition, like recognizing scans, letters, etc. So all of these are examples of how we deal with algorithms as an end user every day. Now, this is just a meme. I don't know if it's true, but I found this on the internet and I just found it funny. So Kylie Jenner asked on Twitter, can you guys please recommend books that made you cry? And here one person comments, data structures and algorithms in Java made that person cry. So studying algorithms and data structures is challenging, but this course will not make you cry. The course will be lots of fun. It will be a tough course, but I'm super happy to teach that course, and we'll do lots of hands-on coding in this course. So we'll be studying algorithms, but I'll also show you how to code them. There will be lots of live coding sessions throughout the term, and we'll be investigating the algorithms together. For me, it was something I always wanted to teach. So when I was a student, I was a teaching assistant for algorithms and data structures and liked it a lot, and always hoped I would be able to teach one day algorithms and data structures. And then when I applied for my professorship here, some 6 years ago or 5.5 years ago, I was asked in the interview what I would like to teach in addition to AI, since AI is my specialty. And they asked me which courses from the foundation courses I would like to teach. And I said I'd be very happy to teach algorithms and data structures. And this proved to be very helpful in my interview because the department struggled finding enough professors that wanted to teach that kind of stuff. So, and then now for the last 5 years, I've been teaching algorithms and data structures here. In the last 5 years, a lot has developed. And something you may notice is ChatGPT is also changing coding a lot. For example, if you have some sorting algorithm, like this is some version of Quicksort. Quicksort is a very efficient sorting algorithm, and we will discuss this in a couple of weeks, or maybe 2 months from now, or something like this. And obviously, ChatGPT can help you with such stuff. You have a well, you have this implementation of Quicksort and you want it to be improved. So ChatGPT will improve it for you and will actually look much neater. You can also even generate tests for your code with ChatGPT and other AI tools. Now, you may be wondering why you should still spend time on this course. So, the way or what we learn in this course is not coding, it's actually how to solve problems efficiently. And we will code those algorithms and data structures, but the coding is only an end product. What I want you to know is how to design efficient algorithms and data structures. And this is some skill you still need to learn how to take very big problems, how to break them into sub-problems, and then solve these sub-problems and put all of it together. So that's what we are doing in this course. And for this, ChatGPT won't help you too much. And I know ChatGPT and other Gen AI tools, they will deliver you fantastic results for all these simple initial algorithms when you study, possibly for much of the coursework in this course as well. But you still need to learn how to build such things on your own, because later when you work in industry and you build more complex algorithms, there's simply much less training data for ChatGPT and other AI tools, so they won't deliver that great results for real-world problems because later when you work in a company, you will not be tasked with all the time to implement Quicksort, rather custom algorithms for your employer based on what your customers requested. And Gen AI tools will not work that well for such problems. They will still support you, but they will not ultimately solve all your problems easily. So you still need to be able to build your own algorithms. But there's just less training data. There's so much training data about quicksort and binary search and linked lists because there's just so much training material on the internet available. So you're still learning a very useful skill in this course. But you can use tools like ChatGPT very efficiently. Maybe when you do your coursework, and I've talked about the coursework sheet in the lab session today. So if you have not attended the lab session today, please watch the recording because I've mentioned the mandatory problem, I've mentioned the exam bonus problem. All of this is something you need to look at, and this coursework sheet is in our iLearn course, and I mentioned it in the lab session today that we recorded. When you have some code sample or you've typed some code, feel free to use ChatGPT to improve your code. You're most welcome to do this because these tools will help you to have your private tutor and you will become even better. And you may even get some explanations of how these algorithms work. And there's a question here about the class sessions. So I'm recording all the lectures, plus the intro to Python today. The lab sessions in the next few weeks, they will not be recorded because there will not be new content taught in the lab sessions. In the lab sessions, you will work on the coursework on your own. And when you have problems, I'm there to assist you. Or if you have any questions on the course, I'll be most happy to help you. But since this is all like individual questions, there will not be any recordings from the lab session. I only recorded the intro to Python today, in which I also talked a little bit about the coursework. And these lectures will obviously be recorded as well. Now, when you look at my lectures, all the lectures I teach here, I always put this map of computer science in the slide deck. This map of computer science is something that appeared maybe some 5 or 10 years ago on the internet, and it provides you with the big picture of computer science, like theoretical computer science, computational complexity, cryptography, computer architecture, AI, and lots of other stuff. I think it's a very good visualization. And what I always do in the beginning of the lecture, like today, I highlight which parts are actually relevant to this course. So I highlight this. You see, I've put in the rectangles, and then I zoom in to the relevant parts. And when I zoom in, we will see what this course is largely about. It's obviously about algorithms. We'll do lots of algorithms. We will also look a lot into data structures. We will furthermore look into computational complexity, so how to build efficient algorithms and data structures. Graph theory will be important as a foundation for our data structures. We will code all of our stuff in Python. And there are some side topics, like we will look into quantum computing, and in one algorithm, we will look into information theory, but it's not the focus of this course. But these are the topics we will investigate. So actually, quite some interesting parts from this map of computer science. So what are my aims and objectives of this class? I want you to get an introduction to the field of algorithms and data structures. I want you to have a good balance of theory and applications. So we'll study the theory, lots of maths, but we will implement the algorithms live and test them and tweak them. You will be able to apply this theory to real problems. And as your career progresses, you will see new methods and new problems. And I want you to be able to transfer the skills from this course to new methods and new problems. And we will also be looking into some current research problems, in particular around AI, quantum computing, and this kind of stuff, and see where the field of computer science is going to in the next few years. In order to take advantage of this course, you should have your skills or your programming skills from the first semester, so you should know coding. In the morning today, we already had the intro to Python. We will need mathematics. If you face any challenges with these prerequisites, there's something that you forgot or you don't remember or just don't know, always ask, and I'll be happy to help in class with mathematics, with programming, or any other foundations that you may need, because I want you to succeed in this course. Now, the course looks the following. We meet for 1.5 hours, 90 minutes of lectures per week. And this lecture is unfortunately on Friday afternoons because we have students from a lot of different degree programs that take this course: cybersecurity, AI, different AI programs, business information systems. And Friday afternoon is the only slot when everyone is free for that. We're doing this lecture online and we record it. And then on Fridays, we have 4 lab sessions. And each lab session is 1.5 hours, 90 minutes. You are free to come to any of these lab sessions. We just have 4 lab sessions because we have 200 students taking this course, or possibly even more. Meanwhile, we have 240 students, so another 40 students joined the iLearn course today. And we need to be able to supervise you in some adequate way, and that's why I have 4 lab sessions every Friday. You can come to 1 lab session, you can come to 2, you can come to all if you wish, but there will not be new content. Rather, you'll be working on the course worksheet, and for any problems or questions you may have, I'm happy to assist. The lab sessions will be hybrid. So I'll be in the classroom, in the lab room, and you're welcome to come there and interact with me and your classmates. However, if you're unable to be on campus, You can also join via Zoom if you have any questions, but there's no lectures or anything in these lab sessions. I'm just in Zoom. Sometimes I'm walking around in the classroom helping students. So if you ping me in Zoom, it just may take a little bit until I'm able to respond because I'm somewhere in the lab helping students with their algorithms. So in total, this is 3 hours, 180 minutes per week. But since most of you are in your second semester, you have come across this unit ECTS, European Credit Transfer System, or whatever it stands for. So 5 credit points for this module. And 1 credit point is an expected workload of 30 hours during the semester. Now, this course carries 5 ECTS, so the expected workload for this course is something like 150 hours. Some students work more, some students work less, I know that, but this is the expected workload. Now, a term is 15 weeks usually. That means you're supposed to spend about 10 hours per week on this course. So just coming to the lab and coming to the lecture is a smaller part of your weekly workload. So ideally, you prepare for class, you check the slides before you come to class, you bring questions, you do revision after class, you do the coursework, you do further readings, you would work on the lab problems from the coursework, and you need to prepare for the exam. And this will be the large part of your work during the week, so not in a classroom, but actually at home or in the library. And most of the content we discuss is available in the slide deck, but I will provide some new stuff on the whiteboard. So I use my iPad and I stream the iPad into the Zoom session to develop some new ideas, to show you some extra stuff, especially some complex mathematical derivations. It's not fun presenting this from a slide deck, but rather I will step by step derive it on the iPad. Now, this course will be examined at the end of the term, and there will be a 90-minute written examination. And this one takes place on campus sometime in early July. The dates will be communicated by the department in the next few weeks. In order to be able to sit the written examination, you need to solve this mandatory problem. I've talked about it in the lab session. It's been recorded, so watch the recording in case you have not been to the lab session. You need to pass the mandatory problem, otherwise you're unable to sit the written exam. If you have done the mandatory problem before and you did not sit the exam or you failed, that's fine. You don't need to retake the mandatory problem. Once the mandatory problem is passed, you can sit the exam. Everything discussed in class is relevant to the exam, but also there are sometimes some slides with further readings in which I refer you maybe to a book or some article. This is also required for the exam. And all the stuff in the coursework sheet could be relevant towards the exam. The coursework sheet is mainly giving you lots of extra practice and better understanding of what we have done in the lecture, with some new problems. And you should work on the whole coursework. Even though almost all problems are optional, there's only one mandatory problem. But this will give you lots of extra practice and you will definitely improve. And this is the best preparation for the exam because sometimes I just copy some problem from the coursework sheet into the exam. And when I mark the exam, I can notice directly who actually attended the lab sessions and worked on the coursework and who did not. I'll say a few words about the exam now. So the exam is a 90-minute written exam that takes place in July. You find all the past exams in my Nextcloud directory, to which I'm referring from the iLearn course. And this is the exam paper from last year. all the instructions and questions are posed in English and German, so they are translated. Ideally, all of you would be answering the questions in English because the course is taught in English because we have students from both German and English language programs in this course. But the questions are also written in German. And in case you struggle with answering in English, you can also answer in German. And any questions you may have in a lab or in a lecture, you can also ask in German if you wish. My exams look the following way. In the exam, we have 3 problems, and each problem carries 25 points. And it's your task to answer 2 of these problems. So the 90 minutes in this year is supposed to work on 2 of the problems. So you can score 50 points at the very most. So this is to your advantage. You can pick 2 of the big problems. We're not looking at the problems now in detail because we're just starting with the lecture. If you have time left, feel free to work on the 3rd problem. And if you work on all 3 problems, only the best 2 problems will count. So ideally focus on 2 problems and don't waste your time scattering your efforts among the 3 problems. I did my master's in England at Imperial College London, a very demanding university. And there I saw this, and the exams were usually 4 problems, and we had to pick 3 of the 4 problems. And I liked that style. But then I asked what would happen if I answered all 4 problems. And then my professors told me that the worst 3 answers would count, not the best 3. So here it's different. First of all, it's 2 out of 3. And if you really work on 3 problems, the best 2 will count. So it's to your advantage. If you look into the course worksheet, I mentioned this earlier today in the lab session, there's also an exam bonus problem. If you pass the exam bonus problem, you will get 10%, so 5 points on top. For example, say you score 40 points, and if in the exam and you have the bonus from the coursework, then you get 5 points on top, so 45 points. So overall, I think this exam, it's a tough exam, but there are lots of points that are to your advantage. Like you pick 2 out of 3 problems, plus there's a bonus from the coursework if you work on the bonus problem. Past exams are available. Every year we have the final exam in the summer term, and in the winter term, we have the resit problem, the resit exam for those who did not do the exam in the summer or who failed it. But now there's one more advice. And there's one student here who writes me that 1 year ago, he did a mandatory problem and a bonus problem. So if you did the mandatory problem and it was added to your transcript, it's fine. But all the students who did the bonus problem in the past, they need to resubmit this year because I'm just unable to track super long Excel files with submissions from maybe 5 years ago. But I will send a round message about this. About how to resubmit if you had submitted this stuff in one of the past years. So this will come sometime later in the term. And these mandatory and bonus problems, they need to be submitted until July the 1st. And so the end of the lecture period is about 1 week after July the 7th. I don't know exactly when I'm just checking this quickly in my calendar. So the end of the lecture period is concretely on July the 11th. And after July the 1st, so July the 2nd, I will very quickly assess all the submissions for the mandatory and bonus problems and then notify you about who has passed and who has not passed. And in case there was any issue with the submission, you may have 1 or 2 days maybe to fix that in case something catastrophically went wrong. but you need to submit until the end of July 1st. So late submissions will not be accepted. And if you don't pass the mandatory problem or you don't submit it, then you will be unregistered from the written exam. And one student asks about the structure, about the time. So you're supposed to do two problems in 90 minutes. Some students need 90 minutes. Some students are fast. They do three problems in 90 minutes. But I would encourage you first to fully focus on two problems of your choice and then do one of the remaining problem if you have time left. Because only the best two count. And here comes now a very important information. Unfortunately, we have students every year who submit the mandatory problem or they try to sit the written exam without having registered for the exam. This creates a huge headache for the admin assistants in the Center for Studies and me because it's lots of manual work to register you and then to add the mark. So you're only able to pass the mandatory problem and get your mark from the written exam if you had actually registered for both. And it's two exams you need to register. One is the actual written exam, and the other one is the mandatory problem. The mandatory problem is often called in Primus something in German like Leistungsnachweis or Übungsleistung or just LN for Leistungsnachweis or mandatory problem. And you need to register for both because every year we have students who submit the mandatory problem, but they didn't register for this in Primus. And it just creates a lot of manual work for the admin assistants and me. So there's also a new policy as of this year. And the policy is in my courses, no registration, no mark. So if you submit a mandatory problem, but you had not registered for it in Primus, your submission will just not be considered. That would also mean you cannot sit the written exam. Registration for these exams is not possible at the moment. This will be possible in Primus later during the term, and you will get an email from the Center of Studies for all of this. But if there are any questions about registering for exams, please send this to the Center of Studies because I don't have any access to Primus or to see where the exams are and what they are named. It should be all very easy for you to find. Maybe you're even pre-registered for some of them if you're in the second semester. But for any questions about registering, please ask the Center of Studies because I have no control and even no access to Primus. I only have access to Primus to add the marks after the examination, and that's it. You don't need to register for the bonus problem separately. The bonus problem is just something you will be submitting via iLearn. And this brings us also to iLearn. So this is our iLearn course. It's the meta course because we have students from a lot of different degree programs. And for each of them, there's a new iLearn course created. And I linked from each of the program-specific courses to one meta course. So I only need to communicate that information once. And in here, you find everything. And down there are also the submissions for the mandatory problem, which no one obviously has submitted yet, as well as the exam bonus problem. But for the mandatory problem, it's a separate examination. So you need to register for this in Primus, as well as for the written exam. And the bonus problem you just submit. And then once I mark the written exams, I will look up who has actually submitted and passed the exam bonus problem. In addition to the lecture and the labs, we also have tutorial sessions. So Meltem, she's one of the students who took this course last year and did terrific. She's the teaching assistant this year, and she teaches tutorial sessions on Tuesdays from 5:30 to 7 p.m. I know it's late, but it's the only time slot in which all the students from the various degree programs taking this course have time. And in this tutorial session, Meltem will be offering some revision of the past lecture. She will discuss questions with you. You will discuss the coursework or additional exercises with her. And she offers this on campus and hybrid via Zoom. And you find a link to the room, which is here in the calendar, as well as the tutorial materials and the video stream. It's all available here in the iLearn course. And if you have any questions, please get in touch with Meltem. There's a question if the tutorial sessions are recorded. This is something you need to ask Meltem because she is in charge of the lab sessions and running them. So I'm not at the lab sessions. It's all done by Meltem. And every year I recruit one of the top students from the current year as the teaching assistant in the following year. And Meltem was one of the top students last year and did great. And she's happy to teach the tutorial this year as our teaching assistant. So, and here I'm highlighting this. There are 2 examinations you need to register for. I mean, the registration is not open yet. It will still happen for the written examination as well as the mandatory problem. There are also some books that are super helpful for this course. So most of this course is actually based on the Goodrich book. So this is called Data Structures and Algorithms in Python, written by Goodrich and 2 other authors. This book is something you can buy. It's quite expensive, but we also have it available as an ebook in our library, and the link to the ebook is in our iLearn course, and you can either access it from our university network or from at home. But from at home, you need a VPN connection to connect to the university for a university IP, and then you can read the ebook. And the ebook is needed, in fact, because many times in the coursework, I've said this earlier today in the programming session, I refer to something like P something in Goodrich or C or R something in Goodrich. These are always problems in the Goodrich book, and that's why you need the ebook and you need to be able to access it to see all of these problems that the coursework is referring to. There are obviously other topics that are not part of the Goodrich book that I'm teaching, but probably like 2/3 or something of the course is somehow linked to the Goodrich book. And the Goodrich book provides you with maybe further readings, more insights, and more details that you're welcome to read. There are excellent other great books on algorithms. I like the Sedgwick book on algorithms. It's a very good book on algorithms. If you want to get a deeper understanding of other algorithms. And we will also look at complexity theory, and there's a very good book on the theory of computation by Sipser. You don't need to buy the Sipser book only if you're super interested in computational theory, theoretical computer science, and complexity. This is a really good book that is very, very practical and explains in detail how certain proofs work. I read this book when I studied computer science. I read that book for my theoretical computer science classes and enjoyed it a lot. And there's a 3rd edition that appeared in 2012, but that's absolutely fine. There's a theory and there's not much changes. The Goodrich book is also from 2013, but this is not a Python course, so we are not interested in the latest Python concepts. Rather, it's a theory course and we apply the concepts and we implement them in Python. But Python is just a tool. It's not a Python course. So the book is absolutely fine from 2013. If you look into last year's recordings, so I taught a course last year, and as usual, there are some minor improvements, and I've added another selected algorithm. So you saw this before in the contents. There is a chapter on selected algorithms. We don't discuss all of the selected algorithms, but every year there are some new ones. So this year I added an algorithm that is called the Bloom filter. Very interesting algorithm that I hope we have time for this year. And in addition to various minor improvements, I've extended the hash table chapter a little bit with a couple of slides on so-called load factors and resizing, because this is something that was underdeveloped last year when one of the students asked, and this year I've added a few slides on an extended discussion. There's a question about the Crocking Algorithms book from Bhargava. That one is fine too. I have it at home. I have not read it in detail, but it's a good book and people like it. So the most important one is the Goodrich book, also with regards to the coursework. In all the other books, feel free to pick whatever you like to maybe get some extra insights or learn about some more algorithms if you wish. We have done the intro to Python earlier today in the lab session, so I'm skipping all of these slides, but what's important, and I've highlighted this in the lab session, do the further readings, read these subchapters from the Goodrich book, in addition to the intro I gave you, and there was actually one more slide at the end of the object-oriented programming introduction. This is also a further reading, and you should read chapters 2.3 to 2.5 to study a few more concepts that you don't need today or tomorrow, but probably in the second half of the term. It will be very helpful if you have studied these a little bit to know how these concepts work in Python, because we will need them for some more advanced data structures. So, but if you're new to Python, maybe read this in a couple of weeks, not today. Focus maybe on the initial Python introduction. Now we have finished the introductory chapter, and I want to know from you if you're all good or if there are any questions. If there are any questions, maybe raise your hand or maybe some sign. If you're okay, maybe send a green sticker. So looks all very positive, and I don't see any questions here in the chat. But if you have any questions later, feel free to let me know. In this graphs chapter, we will lay the foundations for all the other data structures, because all the other data structures are just some type of graph, and we will start with the most generic data structure. In a lot of algorithms and data structures courses, these graphs come at the very end, because you first start with simple data structures and then you get increasingly more complex. And then a lot of courses, they try to generalize this at the end. However, I want to start with the generalization in the course. And the graphs chapter will be challenging. I absolutely admit this, especially two of the algorithms we will look at. This will be quite challenging. And it will take you a little bit and it will give you some headache to study. But I believe if once we start with these very generic concepts and you have understood them, we can just simplify them or constrain these generic concepts to build simpler data structures like lists, trees, maps, and hash tables. But I know these very generic concepts in the beginning are challenging, but I think the learning experience is better in the long run. We will study graph definitions and so-called adjacency matrices. We will see applications in computer science. We'll try to do these three elements here today. And next week, we will look at shortest path and lowest cost and A star very briefly. There are now some questions here in the chat. What's my opinion on when artificial general intelligence comes, or if we cover reinforcement learning algorithms? So this is an algorithms and data structures course, so we will not be doing reinforcement learning. This is something that you would probably see in a machine learning class. And artificial general intelligence is a theoretical concept in which you have an AI that outperforms humans in a wide number of tasks. Because what we see today is AIs that outperform humans in single tasks, or very narrow AIs, but they are unable to do anything else, and an artificial general intelligence, something very wide that would outperform humans on lots of different tasks. We don't discuss artificial general intelligence in this course, yet I think it's super far away because we probably have to rethink a lot of foundations in algorithms, in data structures, in theoretical computer science. So I don't think it will be near anywhere. I think it's right now more like a marketing term, but there's also a lack of that one definition of what artificial general intelligence actually is. And because that definition is not there, everyone may imagine something different. But it's right now, I think, more like a marketing thing. And there are some interesting AI agents, but I don't think this is anywhere near artificial general intelligence. And if you try these platforms for problems beyond their demos, oftentimes it by far doesn't work that well. But this course is not about AI. If Since most of you are interested in AI, there are other AI courses in this program, and I will also be teaching numerous AI courses later in your studies. And for now, I will switch back, or I will switch to the iPad in order to develop some stuff with you on the whiteboard. Recording. If by any chance ever this screen share terminates, all of this has happened in the last few years, please just ping me very quickly, maybe not by chat, just turn on your mic and tell me, because if the screen share terminates, it's something I may not notice while I'm on the iPad. And I want you to have a smooth experience here. Before we look at graphs, we need a math primer. And we will look at the Cartesian product. The Cartesian product of two sets can be defined. So we have A, and then we have this X. It's actually not an X, it's a sign for the Cartesian product of the sets A and B. And this generates a new set. And in these sets, we have tuples, and the tuple has the elements A and B in lowercase a and B, where the lowercase a is from set A, and so this is an and the B is lowercase b is an element of set B. Who of you has seen this before, the Cartesian product? Maybe something you've seen in your first semester. Maybe thumbs up or green sticker if you have seen this. Red sticker if you have never seen this. And since there's at least one person who has not seen that, or now multiple, which is totally fine, we'll do an example. So we have our sets A and B, and what we want is a new set of all the ordered pairs of elements A, B. What's very important, just from the notation, for sets we use these curly braces, and elements in a set are unordered, while in green we have this tuple for which we use parentheses, and within a tuple we have an order. So this is an ordered pair where it's A followed by B, and that order is binding. It's very important you don't mix up the concept of tuples and sets, because this will come with dramatic consequences when we define now various types of graphs. And I want to do an example with you. Say A is now elements 1, 2, and 3, and B are elements X and Y. I want you to provide me in the chat with the result of the Cartesian product of A and B. And once you have your solution, please post it here in the chat. Pay attention to all the notation, like whether you use curly braces or parentheses. We got a first attempt, and that attempt is not following the right notation. So this would be actually not well defined, which we saw in the chat. It's probably, you probably have the right intention, but maybe you want to rethink what it may look like. One person has sent something in the chat, in private to me. You don't need to send in private. And if you get it wrong, if you send it into the public, that's absolutely fine, because we're here to learn, and it will take us a little bit to study these generalized concepts. I'll wait for another response, and then we'll actually compare. The next one that I got in private looks quite good. Very importantly, it's a set that we get. And the set contains 6 elements. One element is 1a, because we take the 1, sorry, not 1a, 1y, because we take the 1 and the x or y. I've picked not a y, but it's anyway, it's a set. Then the next one could be a 1x, then a 2x, a 2y, a 3y, and a 3x. So we have 6 elements, and each element is a tuple or an ordered pair. So we have this one, this one, this one, this one, this one, and this one. The order of these 6 pairs doesn't matter because it's a set. So if I write first 1y or 3x, it doesn't matter. But we need these combinations of 1, 2, 3, and x and y. And this will be 6 combinations, and these combinations are tuples. So it's very important that these are parentheses because that's an order. Here you cannot just put a set, because if you put a set, then the 1 and the y could be in the wrong order because it's not ordered anymore. Do you get that difference between sets and pairs? Where you need to put a set and where it's a pair? Maybe thumbs up or green sticker or red reaction if this is not clear, or if you want to discuss it again with us, because it's very important that you get this. We got a red sticker, and for this person who has a question, maybe you can ask us or multiple, maybe you can tell us where the problem is and how we can support you. Either in the chat or turn on your mic, because we need to understand this. So
I'm sorry, I think it was too fast for me. So if you could just.
Okay. So again, in a set, so we have a set, say P, and we have a set P in which we have elements 1, 2, 3. Then in the set, there's no order of 1, 2, and 3. It's just an unordered data structure. And we cannot have duplicates. So in a set, we cannot have like the 3 double. It's just a set. So one element exists once at the very most, and we have no order. But if we have Q, which is a tuple, we put 1, 2, 3. Then this is a tuple, so we have elements 1, 2, and 3 in it in exactly that order. We could also have, so we could say this is Q1, and we could have Q2, which could be something like 2, 1, and 3. It's a different tuple than Q1 because we have a different order. We could also have Q3, which is 1, 2, 3, 3, which is absolutely fine. because in a tuple, we can have the same element repeating. But in a set, we cannot have repeated elements and there's no order. So this is a fundamental difference of two structures, sets and tuples. And now if we have our sets A and B, so A is clearly a set and B is a set, then if we take our Cartesian product, we said we are creating a new set. That's why, first of all, the result of the Cartesian product is a set. And in there, we will have tuples. The tuples are this thing here of A and B. So A and B are in an order where A must be from set A and B must be from set B. So A and B have an order, but finally we will have 6 tuples because we have 3 elements in A and 2 elements in B. So one combination would be 1x, 1y, and so forth. And we have these 6 tuples in our set, but the order of these tuples doesn't matter. So I could also just flip these 2 tuples, first put 1x and then 1y, first 3x. But within the tuple, the order must be the same. So it's 1y and not y1. Did you get that difference? Maybe the ones who didn't get it before or had doubts, maybe some thumbs up or something, if this helped. So I didn't come up with these concepts. These are just basic mathematical structures. And that's why I felt it's helpful we do the practice of the Cartesian product, because now we're going to build graphs. So we will do now. And one question is if the Cartesian product of A and B is the same as B and A, in general, you cannot just flip them. So B and A is something different than A and B, unless you have some special cases that A and B are the same sets. But since A and B are different sets, these two Cartesian products are not the same, only if the two sets were the same. So then we will look at graphs. And graphs, the most simple graph is a tuple of elements V and E. Now, a graph is a tuple and has 2 elements V and E. And V is a set of vertices. Set of vertices. Sometimes vertices are also called nodes. And in parallel, we can try to build a very simple graph up here in blue. So I'm putting now the vertices. So these vertices can have a number or contain some data. Here it's just here we just have the nodes. They're not connected yet. And the exact position doesn't matter because we're just layouting the graph. So if V is the set, what would V be for this graph? It would be just a set of these nodes, which are just integers 1, 2, 3, 4, 5, and 6. So it's a set because the set of vertices, for the set of vertices, the order of the vertices doesn't matter because it's just vertices. And how we position them geographically in this example does not matter. But now we can connect our vertices in some way. We can say, for example, the 1 is connected to the 2, the 1 is connected to the 5, the 2 and 5 are connected, 2 and 3, 3 and 4, 4 and 5, and 6 and 4. They are connected. And this is something I need to describe in E, because E is the set of E is the set of edges. And I will write this down for our sample graph here, that E is a set, first of all. And in there, we have connections. But as you can see, there's no directions in our graph. So 1 is connected with 2, but 2 is also connected with 1. So there are no directions. Later we will have directions, but for now, we will just look at the simplest graphs. And we can say E is a set, and this set contains something. And the set contains now subsets. Because we have 1 and 2 connected, and we have 1 and 5 connected, but these are sets again, because 1 and 5 are connected, which is the same as 5 and 1 are connected, because there's no direction. Later we will have graphs with connections. And I want you to complete now E and send this to me in the chat, or send this to everyone in the chat, what the completed E would look like for this sample graph. One person wrote what chi would look like. We are not amending chi, so chi will always be this tuple, and v will be referred to in here. And now the remainder of E would be, we have 1 and 2 connected, and 1 and 5. We have 2 and 5 connected. I could obviously write 5 and 2 because it's a set, so the order doesn't matter. Then next we have 2 and 3. We have 2 and 3. We have 4 and 5. We have 3 and 4. And 4 and 6. Hope I didn't miss any of them. So again, 1 and 2 and 1 and 5, 2 and 5, 2 and 3, 4 and 5, 3 and 4, and 4 and 6. So this would be now the definition of this graph, because these edges, they are undirected. But I can provide you now with a more generic definition of what E would look like, because this E here is just for our example. And this V is just for our example. We said V is a set of vertices and E is a set of edges. But how can we define the set of edges? We can say that E, well, not written very nicely. It's all formatted well in the slides. We can say E is a subset of a bigger set. And we can say this big set contains small sets of X and Y, where the tuple XY comes from the Cartesian product of V with itself. Or we'll just keep it now like this. So what I'm writing here is we have the set of vertices. And we take the Cartesian product. And one student just asked, why are we using set brackets for these? It's all unordered because E is a set And in the set, we have the edges, but the edges are not directed. So 1 and 5 is connected like 5 and 1 are connected. That's why in here we use sets. Later we will be using tuples when we actually put directions into this graph. And now I'm saying E is a subset. And there's a question about if a node is connected to itself. I will be coming to this very soon, in a moment. But we first continue with this definition. We will see that we have V has a Cartesian product with itself. So V with itself. And this can actually be written in a slightly different way, then it looks simpler. We can say V squared. And V squared just means V with itself. And we've seen the Cartesian product before, and the Cartesian product will return us all the combinations of V with itself. So 1, 1, 1, 2, 2, 1, 3, 4, 4, 3, 6, 6, whatever. So that all of them are interconnected. And the Cartesian product returns me as the elements tuples. But I don't want tuples. I want to convert this tuple into a set. So I'm saying we have a big set that contains subsets where we have in these subsets the elements xy, and xy come from these tuples from the Cartesian product of V with itself. So this looks more complex than it is. And E is a subset of this. Because typically you would have not connected all the nodes together with each other, but only some of them. Because in our sample graph, not all of them are interconnected, only some. That's why E is a subset of all of the possible connections. And now one student asked, what would happen if we connected a node with itself? This is often denoted like this. Can think about if would something like this be possible at the moment? Maybe thumbs up or thumbs down if our current definition would allow this. Some say yes, some say not. So the question would be, would 6, 6 be possible from the current definition? And yes, it would be possible because 6, 6 would be in this Cartesian product. And such an entry here is actually called a loop. If one node is connected to itself, sometimes it's called a self loop or something like this. It's an edge of a node with itself. But in our initial graph definition, we don't want to allow loops. We will only allow them later. So I need to add something, and I must say xy is from V squared, but x and y must be different. So we're adding this add and say and x must be different to y. And then these loops are not allowed anymore. So I'm deleting these loops. They're not allowed anymore. Later we will allow loops, but for now we don't allow loops. So we say x and y must be different. And we've seen this example graph, and we don't want to allow loops for now. but we see that E is a subset of this one here. So the tuple the tuple xy comes from V squared, so the Cartesian product of V with itself. But we don't want tuples, we want subsets because the direction doesn't matter. So we convert the tuple into the set, but we only take the tuples for which x and y are different. And this is a so-called undirected graph. Undirected graph. And one question was again about the V squared. So remember, V squared is the Cartesian product of V with itself. It gives us all the possible connections, but all of these possible connections are directed because they are tuples, and we want to convert these tuples into sets so there's no direction. But we only take the tuples for which x and y are different. And actually, so far we have worked with undirected graphs, because later we may also add some direction in a graph, that one direction is from one graph, from one edge, from one vertex to the other, so the edges are directed. But right now we're not thinking yet about that. Very importantly, a graph in context of this chapter refers to this structure. A graph does not mean like a bar chart or a function plot, because this is something else that is often referred to as a graph when you have bar charts or function plots. But in this case, it just refers to this mathematical structure. And this mathematical structure is the basis of all of our data structures. We still have a little bit of time, and we will do now so-called adjacency matrices. An adjacency matrix is a matrix representation of a graph. So one possible definition of the graph is, we say the graph is a tuple of V and E, where V is the set of vertices and E is the set of edges. But we also can define a so-called adjacency matrix. And I'll show you how this works. So we have a sample graph. We have our vertices 1, 2, 3, and 4. You can take this home as an exercise and try to describe this graph with this definition here, and we'll come back next week to that definition anyway. But we can also describe this as a matrix by using the adjacency matrix. And the adjacency matrix for this graph would look something like this. It's a 4 times 4 matrix, and I'm just adding some comments to the rows and columns. And when two nodes or two vertices are connected, I put a 1 in there. So 1 and 2 are connected. So 1 and 2 are connected. But 2 and 1 are also connected. So I put a 1 here. The 2 is also connected with 3 and 4. And 3 and 4 are connected with 2. So 3 and 4 are connected with 2. 3 is connected with 2. And 4 is connected with 2. And all these other entries are 0. So this is our adjacency matrix for this graph. And as a take-home exercise, you can try to describe this graph with an adjacency matrix. And this graph here, you could try to describe in terms of V and E as we have done it before. It's a good practice for you. What I said is the notion graph should not be confused with bar charts or function plot. So one student asked what's a function plot. So a bar chart would be something like this, say you have some counts of something, like maybe some age group, like people who are 5 to 10, 10 to 20, or greater than 20, and you would have a count here. So this would be some bar chart where this is maybe 100 people, 50 people or something. Something like this is a bar chart. Sometimes they are also called graphs, or sometimes function plots are called graphs. So we have a function f of x, where we have something like this. This is also sometimes called a graph. And bar charts and function plots are called graphs, but they have nothing to do in this context with the graphs, which are this mathematical structure. And there's one question about how we store graphs in a computer, if there are also some kind of lists. Well, there are many ways to store graphs in a database. You can represent them as lists, you can represent them as dictionaries, you can represent them lots of different ways, but this is something we'll discuss probably in one of the next lectures when we see, or in the next lecture, we see one format of how we can store these graphs. So your homework is that you need to be able to map between the adjacency matrix and this formal graph notation. And if you take a look into our slides, to which I'm just switching back, you find all of what we have done now in the slides. So we've looked at the Cartesian product. The example is something I came up with spontaneously. You don't find it in the slides. You find this graph definitions, and a graph is a tuple or ordered pair V and E. And this is the example graph in the slides, and we have written down its definition. We have seen it's an undirected graph. We'll see next week directed graphs, and we've seen adjacency matrices. And what you may notice as well is for this graph, it's an undirected graph. So you will find some pattern in this adjacency matrix. In fact, the adjacency matrix is symmetric. So if you calculate its transpose, meaning you just flip it along the diagonal, it's the same matrix. So that's a symmetric matrix for undirected graphs. Next week, we'll see directed graphs, and then that property does not hold true anymore. So if the graph is undirected, the adjacency matrix is symmetric. Next week, we will have 4 lab sessions in the morning and afternoon, and then we'll have this lecture as usual at 3:45 to 5:15. And next week, we will look at more graphs. So it's very important that you're okay with the definitions we have looked at today, so that you are able to, that you understand tuples, that you understand Cartesian product sets, and that you're able to convert between the formal graph definition and the adjacency matrix. And next week, we will take all of this and step by step amend it. So you see, we will look then at undirected graphs that permit loops. We will look at directed graphs. We will see directed graphs permitting loops. We will even see weighted graphs. So we can have weights for these connections and directed graphs. And all of that is not that difficult, but you need to understand all the concepts we have studied up to today, because next week we will look at these. We will look at applications of graphs. And we will look at graph algorithms. So make sure you're familiar with these concepts. There are some questions here. If you find the slides on iLearn, in the iLearn course, I have shown you there is a link to my Nextcloud directory. And in the Nextcloud directory, you find the coursework, the slides, past exams, and all of this. And there's a question about the content on the groups on Fridays. So there is no content of the lab sessions. Again, I've mentioned this before. In the lab sessions, you are working on the coursework, and you ask me any questions you may have on the course, on the coursework, and I'm happy to help. So each lab session is different. It depends on your input. but we are not discussing new lecture content. And there was one question about about the mark of the exams. I'll be happy to talk about this. Just opening the corresponding file. Just give me a quick second to find that file. So if you look in my Nextcloud, there is a file that is called Details on Marking of Exams Papers, where I again describe you pick 2 out of 3, the best 2 count, and then you can score up to 50 points. Say this student here scored 24 points, 5 and 20, so the best 2 would count, it's 44 points. But you still get a bonus of 5 points on top in case you have done the exam bonus. You would have 49 points. And how does that mark get, or how does points convert into a mark? I have a formula. I say 60 minus your score divided by 10. So if you score 50 points, 60 minus 50 is 10. Dividing by 10 is a 1.0, the best mark possible. And this score here would include your bonus. And what does that look like for all the other points? Say you have 49 points. This would be a 1.1, but we only have valid marks 1.0, 1.3, 1.7, 2.0, and so forth. So we always round this to your advantage. So a 1.1 would be a 1.0. 48 would be a 1.2, would be a 1.0. If you have 47 points, including the bonus, this would be a 1.3. 46 points is a 1.4, which would be a 1.3, and so forth. So for example, if you score 40 points in the exam and you don't have a bonus, this is a 2.0. If you have the exam bonus, you have 45 points, and the 45 points is 1.5, which gets rounded to your advantage to a 1.3. How many points do you need to pass? 20 points. And one thing is important, the exam bonus will not lift you out of the failing range. So if you score 18 points, the bonus will not help you. The bonus will only help you in order to improve your mark once you have passed. But you need at least 20 points out of 50, so 40% to pass. And then the bonus applies if you have done the bonus. Which coursework problems can you do up to here? Maybe focus on the Python primer. We've done the intro to Python today, which is the Python primer in the morning. Make sure you're familiar with Python, do the extra readings in the book, do the problems here. Next week in the lab, so we always have the lab before the lecture. So in the lab, you can ask any questions about whatever you want, but probably focus on the Python stuff. And next week, we continue with the lecture. And once we have finished the lecture next week, you can continue with problem 7.1. But we don't have enough content yet because we still need to advance with graphs and graph algorithms. And there's a question, well, we can already answer this question, so I'm happy to talk a little bit longer. In what cases are these graphs used? So graphs are a fundamental data structure, so lists or trees, they are just graphs with some extensions or with some constraints. But you need graphs all over in computer science. For example, graph algorithms. For example, in routing, like shortest path, lowest cost, Dijkstra, that you have cities that are connected and you want to know how to get the quickest from one city to another. There are other problems like the traveling salesperson or traveling salesman problem. You have a network of cities that are interconnected, and you're starting in an original city, and you want to know what's the shortest possible route to visit each city and return to the origin. There's also dependency resolution. Dependency resolution means maybe you have a Python package and it needs to import lots of other Python packages. And you're wondering in which order you would actually import them. This would be topological sorting. It's a different graph algorithm. Um, in computer graphics, you have polygons. So polygons are points or pixels, maybe, or not necessarily pixels, but points in your computer graphics world. And you want to know if a point is within the polygon. So a polygon is just a graph in which you have edges connecting the nodes or vertices, and you now have a new point. You want to know, is that point within the polygon? These are fundamental algorithms in computer science, but there are real consequences. For example, a neural network is also a graph. So if you want to train a neural network, you just need some very sophisticated graph algorithm. There are knowledge graphs to combine knowledge in knowledge bases, and you may want to make some inference. You can do that with graph algorithms. A blockchain is a distributed ledger, which is just some graph of blocks. You can also find cliques in social networks. So a clique would mean it's within a graph, a subgraph, which are just nodes that are all interconnected. So like a friend circle, because within this clique, everyone is friends with each other. And you have a huge social network, and in it, you want to find the cliques. So which nodes actually belong together, and they all are interconnected and they are friends. So you see, graphs are actually super helpful or super necessary to computer science. So for the student who asked as a general question, in when cases graphs are used, is this some answer that has helped you? So for the student who asked this, maybe you can just answer if this answer helped. I wanted to discuss this next week because we were running out of time, but I'm happy to speak a little bit longer. And next week, we just look at more complex graphs. For example, we look at weighted graphs. So connections have a weight, which could be maybe the distance in a city between cities. And we want to find the shortest route. The question is, how long does this take to be uploaded? So once I finish this Zoom session, Zoom needs about 10 minutes for creating the final recording, just converting the temporary recording into the final one, and then I upload it to YouTube. YouTube sometimes needs half an hour or 1 hour to process it, and then it will be live. So sometime later in the evening, it will be live, because now I'm in my office still. If I leave, I will already upload it now on YouTube, but it will then only be processed when I'm at home in half an hour or 1 hour. And then I try to make it public as quickly as possible. So it will appear later during the evening. Is that fine as a waiting time? If you need to wait a little bit for the uploading, because it also depends on Zoom and YouTube until it's processed. And there's one question about the mandatory problem. At what level you can work on this. So if you asked this question, I guess you had not attended the lab session today, in which we did an intro to Python. And I said, once you feel comfortable with Python, you can work on the exercise anytime. So P13.50 is from the Goodrich book. It's a project about pattern matching algorithms, which we don't discuss in the lecture. You need to read a few pages in the book about the pattern matching algorithms and then implement them and do a couple of other things like write a report. You can do this in a group of up to 4 students, but I've discussed this in detail today in the lab session. So feel free to look at the recording. The recording is already on YouTube, and I've linked to the new YouTube playlist for this year from the iLearn course. And I've also linked to last year's recordings. This year, for the exam, the content we are doing this year is relevant. But if you sort of want to peek what could be happening in the next lecture, just look at last year's playlist. Are you supposed to work in English? If you write your report in English, I think it's a good practice. You can submit it in German if you wish. The exam is in both languages. But since we're doing the lecture part in English, it's probably good practice for you to write your report in English too. It's certainly a skill you will need for your future career. And with there not being any further questions, we are done for today. Make sure you're fine with these notations. and we will continue with more graph types next week and then look at graph algorithms. Have a good weekend. Take care and bye-bye.